Hello students, welcome to Educate. In the last video, we have started the periodic trend in D block elements. About what is D block elements and other phenomena, we have also discussed in the previous videos. Who have not watched this video, may go to that video and may watch that freshly. That will be too much beneficial for everyone who be prepared for 12th board examination, the NEET examination, the IIT main examination, as well as for CUET examination. That video will be also beneficial for those guys. Now let's see. Now in the predict trend, we will discuss about ionization enthalpy. Previously we have discussed about melting point and size of atom, enthalpy of atomization, which had the same physical periodic trend as was in melting point. Let's see here ionization enthalpies. Guys, you know already the ionization enthalpy. First of all, okay, let's see what is ionization enthalpy. Ionization enthalpy. So what is ionization enthalpy? Any atoms there, suppose sodium here, how much energy will have to provide to loosen the most loosely bonded electron from the sodium? How much energy will have to provide here? Energy will have to provide. How much energy will have to provide to loosen the most loosely bonded electron from sodium? Then this amount of energy will be called ionization enthalpy. Here that will be Na plus, not electron. How much energy will have to provide so that the sodium in the isolated gaseous atom here, this is here isolated gaseous atom of sodium, and how much energy will have to provide so that the isolated gaseous atom of sodium will loosen the electron. That will be called ionization enthalpy. So ionization enthalpy is the amount of energy required to release the most loosely bonded electron from isolated gaseous atom. That is called ionization enthalpy. In the 12th board examination, question will not ask what is ionization enthalpy. But if you will not know what does mean the term ionization enthalpy, then how you will think about that or the phenomena in which the ionization enthalpy plays a significant role. So firstly, let's see here, ionization enthalpy is the amount of energy required to release the most loosely bonded electron from an isolated gaseous atom. That is called ionization enthalpy. Okay, simply here. So in the no need to mug up, try to understand only this one. So ionization enthalpy is okay. So ionization enthalpy is the amount of energy required to release most loosely bonded electron from an isolated gaseous atom. Okay, that was about the periodic trend. Keep in the mind always Suppose when you will have to release one electron from sodium, that will be called first ionization enthalpy. And then after from this Na plus, when you will have to release the other electron, this actually don't exist, but even though to teach you I am here writing this one. Again, how much energy you will have to supply to release this electron, that will be called second ionization enthalpy. In the same way, here when how much energy you will have to supply so that this Na2 plus will convert it to Na3 plus, that will be called third ionization enthalpy. It will be third ionization enthalpy at H2, that means second ionization enthalpy, and here first ionization enthalpy. Another example I am taking which is relevant, that is about the iron. This iron here, when you will provide the energy, so here delta H1 I am writing. When you will provide the energy to this atom, then this iron atom will convert into Fe plus, and during that course the amount of energy required to release the most loosely bonded electron from iron atom, that will be called first ionization enthalpy. Again, how much energy you will have to supply so that the iron atom will release second electron. That means after the formation of Fe plus, there will be formation of Fe2 plus, and how much energy will require to release the electron from this Fe plus, that will be called second ionization enthalpy. And in the same way, how much energy you will have to supply to the Fe2 plus to release the electron from Fe2 plus, that will be called third ionization enthalpy. Here, so from the iron atom, you have how much energy you have to supply to release the electron, that will be called third ionization enthalpy. So this one first ionization enthalpy, second ionization enthalpy, and third ionization enthalpy. Guys, you will have to remember that delta H1 will be least, then after will be delta H2, and then after will be delta H3. Because by providing delta H1 energy, which electron is most loosely bonded, that will get released. After that, the other electron which will be bonded to the iron Fe plus, that will become more tightly bonded with the nucleus, and hence you will have to provide more energy to release this electron. So in any particular element you consider, so always delta H1 will be least, then after delta H2, and least and highest will be delta H3 for any element. Obviously here this one, and in the same, this is an example, in the same manner for the other elements, delta H1 will be least, then after delta H2, and highest will be here delta H3. Okay, one point, this one keep in your mind for any element, this one. Okay, this concept is not difficult, but usually the students do the mistake, and particularly when they solve the MCQ question, they do the mistake. So keep in the mind, for any element, either iron or manganese or zinc, whatever be that, always the first ionization enthalpy will be least, and the third ionization enthalpy here among first, second, and third, the third ionization enthalpy will be highest. Okay, now let's see here about the periodic trend in D block elements. As you will move across the period, generally the ionization enthalpy increases. On moving across the period, the ionization enthalpy increases, but there is a number of exceptions. About those exceptions we will discuss right now. Okay, so let's see here. Firstly, scandium. So what happened? Ionization enthalpy is based on the outermost electronic configuration. Yes, the ionization enthalpy will be based on the outermost electronic configuration, because when we will have to provide the energy, firstly the electron of outermost cell will release. Here don't be confused that since the last electron enters in 3d orbital, that's why electron will release from 3d. 3d, the last electron will enter into 3d orbital, but the first electron will release from 4s orbital. First electron or the second electron. First electron and the second electron, if there is electron in the second, if there be second electron in 4s orbital. If there be the electron in second, or if there be the second electron in 4s orbital, then the first electron as well as the second electron will release from 4s orbital, since 4s orbital is the valence shell. Always electron will release from valence shell. So let's see firstly, write the electronic configuration, and where there may be variation in the ionization enthalpy, where there will be exception in the ionization enthalpy, we will discuss. Okay, so scandium here, I am writing here the total electronic configuration of scandium, and then after there I shall write only the outermost electronic configuration, because the ionization enthalpy will depend only on the outermost electronic configuration. So let's see here scandium. So energy level is 1s2, 2s2, 2p6, 3s2, 3p6, 4. Like that you have arranged the electron, 3d1. Like that you have arranged the electron, but then after you will have to arrange the electron according to cell wise. So that will be like this. In third cell there is 2 electron in 3s, 6 electron in 3p, and 1 electron in 3d. So total how much electron? Now here I am showing you also the number of electron according to their cell. So in first cell there is 2 electron. In first cell there is one subcell, that is S, and there is 2 electron in S subcell. So in first cell there is total 2 electron. In second cell there is 2 subcell, that is S and P. So 2S and 2P, out of which there is 2 electron in S subcell and 6 electron in P subcell. So total number of electron will be here, this 2 plus 6, that is 8. In third cell the number of electron is here 9. How 9? Because the third cell contains 3 subcell here, out of which there is 2 electron in S subcell, 6 electron in P subcell, and 1 electron in D subcell. So total number of electron here is 6 plus 2 plus 1, that is 9. And in third cell there is only 2 electron. That is the electronic configuration of scandium. So scandium, outermost electronic 3d1, 4s2. Then after for the next element, in titanium, the last electron will enter in 3d. So everything will be same. Here that will be 3d2 and 4s2. Same. In vanadium, the electronic configuration will be 3d3, 4s2. Okay. So let's see here about the scandium. The outermost electronic configuration will be by watching this electronic configuration, then what's written in this your NCERT book, you will not feel any necessity to read them. But you read once and you will realize that you can predict by yourself also. Whatever written here, you can predict also. So first one here, generally on moving across the period, the first ionization enthalpy, then after will be second ionization enthalpy and third ionization enthalpy. Generally on moving across the period, the ionization enthalpy increases. About that you might have studied in periodic table. On moving across the period, the ionization enthalpy increases. Why increases? Because on moving across the period, the atomic number increases. Atomic number increases means number of proton in the nucleus increases and the added electron enters in same cell. Since on moving across the period, the atomic number increases, so the number of proton in the nucleus will increase and the added electron will enter in the same cell. As a result, the attractive force between the nucleus and the valence electron will increase. The attractive force between the nucleus and the valence electron will increase, so the valence electron will displace towards the nucleus and hence the atomic radii or the atomic size decreases. Okay, and about the ionization enthalpy based on the electronic configuration. So what happened on moving across the period? Ionization enthalpy increases. Okay, why increases? Because on moving across the period, the atomic size decreases. Okay, now there will be exception. So let's see here, in case of chromium, here this chromium 4s1 and 3d5. So if chromium will lose one electron, then their outermost orbital will be half filled, because d subshell contain 5 orbital and all the orbital will be singly occupied. So the outer valence orbital of the chromium will become half filled, which will provide extra stability to the chromium. As a result, the first ionization enthalpy of chromium will be less than expected. Okay, so first one is here, the where is here first, then after come here at the copper. In the copper, the first ionization enthalpy will be also less, because after losing one electron, the valence orbital of copper will be fully filled, which will provide extra stability to the copper. So second one will be only points you will have to keep in the mind. Reason you know already, this one. Okay, then after let's see about the second ionization enthalpy, that point here. Now let's see the second point. Now we will discuss about the second ionization enthalpy. So after losing the electron from these elements, when these elements will release one electron, then what will be the electronic configuration? So let's see here. Everywhere there will be one electron. So no need to write about this one also. Now consider about this one. So now in this electronic coefficient goes on the manganese. If manganese will release one electron, then when manganese will release one electron, then the valence orbital of the manganese will be half filled, which will provide extra stability to the manganese. When manganese, now after releasing one electron also, there will be a positive charge to every element. This is the electron. This is the electronic configuration of this ion. So if manganese Mn plus will release one electron, then its outermost orbital will be half filled, which will provide extra stability to the Mn2 plus. So that's why second ionization enthalpy of manganese will be less than expected. So that means if after releasing the electron, the species formed will be stable, then this element will have greater tendency to release that electron. Okay, so first one is here. Same here, come to the zinc, and in this case the second ionization enthalpy of zinc will be lowest, because the valence orbital of the zinc Zn2 plus will be fully filled d orbital, because the valence orbital of the zinc Zn2 plus zinc ion will have fully filled d orbital, which will provide extra stability to the Zn2 plus. So second ionization enthalpy of zinc will be very, very high. Okay. What's the reason? You already know about the reason, and I don't think so that need to write about the reason. Okay, extra stability because Mn2 plus will have extra stability, here Zn2 plus will have extra stability. Even though if anyone would like to write, may write. Then after, let's see about when these elements will release one electron again. So what will be there from 4s? No electron will be there. Then after, the electron will have to release from the d orbital, here scandium. If that will release one electron, then if scandium will release one electron, then the scandium Sc3 plus will have noble gas electronic configuration. So scandium Sc2 plus will very frequently release the electron. That means scandium will release the third electron by providing less amount of energy. So the third ionization enthalpy of scandium will be very less than expected, because the Sc3 plus will acquire noble gas electronic configuration. Now let's see increases, and here 3d4 here. Manganese very high, because because manganese already have half-filled d orbital. So after releasing the electron, its stability will decrease. So that's why the third ionization enthalpy of manganese will be very high compared to expectation. So second point is now manganese come, then after comes about the iron. Iron here 3d6, 3d6 like this one here, and 3d6, so 5 orbital here, and this one here. So if Fe2 plus releases this electron, then it will have half-filled d orbital, which will provide extra stability to the ion. So that's why the third ionization enthalpy of iron will be less than expected, because after releasing one electron, after releasing the third electron, the Fe3 plus will acquire half-filled d orbitals, which will provide extra stability to the Fe3 plus. You might have aware about that. The Fe3 plus is more stable than Fe2 plus. So anyhow, it takes times to form FeO. Whenever there be formation of FeO, that means ferrous oxide, then very easily the FeO converts into Fe2O3 like this one. Now here iron done. Then after just goes on this copper after releasing 2 electron here. There 2 electron. After releasing 2 electron, the copper will have the D9 configuration. So now zinc have already fully filled d orbital. So zinc will have less tendency. There will be so much requirement of energy to loosen the electron from Zn2 plus, which is not available, practically not available at room temperature. So that's why zinc shows only one oxidation state, that is +2. I have taught you earlier also. Zinc shows only one oxidation state, that is Zn2 plus. So here, that is next one is so zinc don't show more than +2 oxidation state, because to release the third electron from the zinc there will be so much requirement of energy that practically that much amount of energy don't get by the zinc. So that's why zinc don't show the ionization enthalpy of more than +2. Okay, so that was very easy. This one when you will then after, when I have taught you in the NCERT book, there is has been written, and I think when you will read this book NCERT, then you feel difficulty to understand this one. So better will be firstly listen the lecture of this educate, and then after you go through the book, then you will feel easier to understand. Now let's see oxidation state. Oxidation state here. What you have seen here? This is the table of the oxidation state shown by the 3D series. The elements of 3D series, this one. And here you watch out, the scandium shows only one oxidation state, that is +3, and zinc also shows only one oxidation state, that is Zn2, that is +2. Scandium shows only one oxidation state, that is +3, and zinc shows only one oxidation state, that is +2. Now titanium +2 and +3, +2 and +3, +4, +5, vanadium, like this one. So one point have you noticed here? Have you noticed one point? That the oxidation number of a particular element vary through unity. In case of p block element, the oxidation number shown by any element will vary through unit 2. That means suppose let's see about the phosphorus, group 15 elements, or nitrogen you may also take. So group 15. Phosphorus, just say, watch out here. So phosphorus shows the oxidation state of -3, then after +3 and +5. So oxidation state shown by the phosphorus will vary through 2 units here. Same here when you consider about the sulfur. So sulfur shows the oxidation state of 1, negative oxidation state also shown by the sulfur since it is the non-metal. So that's why sulfur shows the oxidation state of -2, then after +2, +4 and +6. So here the oxidation state shown by any particular element vary through 2 units, while in case of D block elements, the oxidation state shown by a particular element varies through unity. So one point keep in the mind. Firstly, okay, one point is that. Now let's see here. Scandium and zinc shows only one oxidation state, that is +3 and +2 respectively. Then after, the number of oxidation state shown by the transition elements increases, like titanium show +2, +3, +4, vanadium +2, +3, +4 and +5, chromium +2, +3, +4, +5, +6, and manganese +2, +3, +2 to +7. And then after, the number of oxidation state shown by a particular element, that it starts decreasing. Iron, this one shows cobalt, nickel, copper. This is very here. So one point here is, second point is here, scandium and zinc shows only one oxidation state. Now about this point, when you move across the period, the number of oxidation state shown by any element firstly increases and then after become maximum at the middle and then after decreases. Why? Because the added electron enters in d orbital. Here the added electron enters in d orbital. So the number of unpaired electron firstly increases, become maximum at the middle, and then after starts decreasing. So the number of oxidation state shown by any particular by the elements, that will firstly increase and then after decrease. This year in 2025 there was a question, you watch out, the question of this 12th board examination, that there was a question that which transition metals show highest number of oxidation state in 3D series. In 3D series, question was in 2025. I am not telling you word by word. You read the question of this year and you watch out. That's what is there. So question was, in 3D series, which element shows maximum number of oxidation state? So obviously Here you have washed out the manganese show maximum number of oxidation state, and that is from +2 to +7. That much. In whole of the periodic table, in the 12th board examination, question will be only from the 3D series. But in case of NEET examination or in IIT examination, as well as in CUET examination also, the question may ask from whole of the periodic table. So in whole of the periodic table, the osmium that goes to the periodic table, which I have told you to draw. Osmium lower than manganese shows highest number of oxidation state, and that will be for osmium, that will show the oxidation state of +2, +3 to +8. Here 1, 2, 3, 4, 5, 6. Manganese shows the 6 oxidation state, and the osmium not like this, and the osmium shows +2 to +8, that is 7 oxidation state. Okay. Now then after is about in this NCERT book also, here the which oxidation state will be most stable, and you can predict about that also. So among scandium only one oxidation state, so no controversy here. Titanium, that is +2, 4 oxidation state. Why? Because when you will write the electronic configuration of titanium, that will be 3d2 4s2. So in +4 oxidation state, all the 4 electrons released from the titanium. So after releasing all the 4 electrons, the titanium will acquire noble gas electronic configuration. That's why titanium will show the stability of Ti4 plus will be maximum. That means stability of titanium in +4 oxidation state will be maximum. Now in vanadium, same, vanadium 5 +5 oxidation state will be maximum vanadium. Now let's see about the chromium. So here 1 electron will release from here and 2 electron from here. So that will be 3d3, and so in chromium in +3 oxidation state, the electronic configuration will be 3d3. One concept about which you will aware later on, I am telling you. Listen, what happened? We generally know that all the orbitals of a particular subcell are degenerate. That means here the name of this orbital is, this one is dxy, here dyz, dxz, dx square minus y square, and this one is dz square. And we generally know all the orbitals of this d subcell are degenerate, means the energy of all these orbitals are same, but the degeneracy of the d orbital, when that will be the valence shell, the degeneracy of the d orbital do not maintain for a long period. It dissociates into the energy of these 3 orbitals, dxy, dyz and dxz. That decreases, and that is called T2g energy level. And the energy of these 2 orbitals, that is dx square minus y square and dz square, that increases. That is called Eg energy level. Now T2g energy level here is half filled. In case of chromium, in +3 oxidation state, the T2g energy level is half filled, which will provide stability to the chromium. So that's why in +3 oxidation state, the chromium will be stable, and in +6 oxidation state, that will be also stable, because all these electrons will lose out and the chromium will have noble gas electronic configuration. Same as in case of manganese. Manganese in +2 oxidation state, that is stable, because in +2 oxidation state its valence orbital will be half filled, and in +7 oxidation state it will acquire noble gas electronic configuration. Now iron +2 oxidation state stable, and +3 oxidation state due to half filled d orbital, that will be stable. Same cobalt +2 and +3 oxidation state, nickel and copper. In case of copper, +2 is more stable than +1. Why? We will discuss later on also. And zinc, only one oxidation state. Okay? But listen here, in Cu2+, okay, about that concepts I shall tell you later on, because this video has become already long. So about that, why there is Cu2+ is more stable, and that will come later on also. That is in standard electrode potential. So today it's all for this video. In the next video, we will discuss about the standard electrode potential and the standard electrode potential. Okay, it's all for this class. Thank you, Team Educate.